Great, thank you. Welcome everyone to the next Gen 4 International Forum webinar presentation. Before we get started, I do want to do a few topics of housekeeping sort of topics. The first of which is in the download PowerPoint pod. If you click that, the slide deck is available to download directly to your computer station, and you are welcome to do that. Today's presentation is being recorded, and that archive will be posted on the Gen 4 website, and that link will be available when the thank you notes go out today. And last but not least, there is a link to a survey. We do take appreciate your feedback, and we take your comments very seriously. So if you have comments on the presentation today, ideas for upcoming presentations, anything of that nature, we appreciate that very much. The questions we will take at the end of the presentation, and you can type those into the Q&A pod. We will take as many questions as we have time for. And with that, let's, no further ado, we'll get started with today's presentation. Doing today's introduction is Dr. Patricia Pavie. She is the Director of the Office of Material and Chemical Technology within Department of Energy, Office of Nuclear Energy. And she's also the chairperson for the GIF Education and Training Task Force. Patricia.
Thank you very much, Bertha. Good morning, everyone. It's my pleasure to have Dr. Robert Berry with us today. He received his doctorate from Brandeis University. He is currently a scientific advisor at the Brookhaven National Laboratory. He has over 40 years of experience in nuclear energy research. He has performed studies on safety, security, non-proliferation of advanced nuclear concepts. For 15 years, Dr. Berry was co-chairman of the Working Group on Proliferation Resistance and Physical Protection of the Generation 4 International Forum. He has served on the board of directors of the American Nuclear Society and as president of the International Association for Probabilistic Safety Assessments and Management. Dr. Berry was awarded the Theo Tommy Thompson Award in 2003 by the American Nuclear Society. In 2004, he received the Brookhaven National Laboratory Award for Outstanding Achievement in Science and Technology. He is a fellow of the American Nuclear Society and of the American Physical Society. He has participated in risk-based standards development for nuclear technologies for more than 2 decades. So without any delay, I'm going to give you the floor, Bob. I wanted really to thank you for giving this webinar. Bob retired just a few months ago, but still very active and willing to present this webinar. So thank you again, Bob.
And thank you, Patricia, for the very kind introduction. And thank you to all the participants in this presentation. Some of you it's very early in the morning, and for some of you it's very late. So thank you all for your willingness to come and listen to this presentation. So as an introduction, I want to note that as we embark on a path towards growing number of nuclear power plants worldwide, it's important to consider the goals of Generation 4, the 4 top-level goals. And they are sustainable nuclear energy, economically competitive nuclear energy, safe and reliable systems, and the focus of this presentation is the 4th goal, proliferation resistance and physical protection, which I'll be referring to sometimes as PRPP or PRMPP, because it's certainly a mouthful to say all of that. So as we think about moving forward in these 4 areas with the designs of the new Generation 4 systems, let's look at sustainability and getting that right. What's important there, of course, is a reliable fuel supply and the waste issues. And that's independent of whether we have an open fuel cycle or the closed fuel cycle where we reprocess and recycle. So it's very important to assure that we have fuel and can dispose of the waste at the same time, or in the course of the nuclear enterprise, I should say. So economics is another very important aspect for nuclear power, and we need to get that right, of course. And we have an economics modeling group of the Gen 4 organization, and they're working very hard to assure that there are methods for getting to an economically robust and competitive nuclear power situation worldwide. But of course, we see that to be cost effective, we've got to be mindful of the fact that we have seen cost overruns with nuclear power. We have seen bankruptcy recently with nuclear power, particularly in the United States. That was a rather hard blow. And third, we need to assure that nuclear power is competitive relative to other sources of generating electricity. Going the wrong way there. Okay, third, we need to think and assure that we get the safety picture right. And fortunately, again, we have a working group within Gen 4, the Risk and Safety Group, who's working on that, developing an approach to assuring safety and building safety into the design process for Gen 4 systems. And as we proceed with that, and as they've been developing their methodology, they've been very mindful of gathering the lessons learned from the 3 Mile Island accident, the Unit 2 in Pennsylvania in 1979, the Chernobyl accident in the former Soviet Union, 1986, and the Fukushima accident in Japan in 2011. So they are working to assure not only safety but reliability as well. Our mission is getting PRMPP right, and the story there is very simple. It's one picture is worth more than 1,000 words. We just must prevent what we see in this picture. So what I'm going to talk about today in this webinar, 4 things connected with the working group. One is, what are we, the PRPP group, Gen 4, I've already hinted to it a bit. A little bit about our methodology, what we came up with. Then thirdly, I'll talk about the case study that we did to help illustrate the methodology, and it was very important as we developed the methodology to have that case study working hand in hand with methodology development. And fourth, I'll say something about our interaction with the Gen 4 designers, the 6 Gen 4 design concepts that have been proposed a decade and a half ago and have been worked on very diligently by many, many people over the course of the time. And ultimately, the reason why we need to talk about that, of course, is that they are the ultimate owners of our methodology, and the use of this approach, this Gen 4 approach, is key towards assuring PRMPP for the future designs. So at the outset, I should note that we've taken on 2 missions within the PRMPP activity. One is assuring proliferation resistance, or at least assuring that we have a methodology for it. And second is physical protection. And these are distinct activities. And in fact, if we had been assigned from the get-go to take on one or the other, either one would have been enough of a job for us. They're both very important topics, but they're distinct topics, and it's important to recognize that distinction. Proliferation resistance refers to the situation in which the host state is the adversary, a host state of a Gen 4 system, then it goes forward to do malevolent things with the Gen 4 system. And that is indicated here as connected with diversion or undeclared production of nuclear material or misuse of the technology leading to weapons or other nuclear explosive devices. On the other hand, physical protection is a case where the host state is now the defender, and there is a subnational entity or non-host state actor a terrorist perhaps who is trying to either steal material or sabotage it for the purpose of gaining nuclear explosives or radiation dispersal devices. So there are these two, and they are distinct. So we've had more of a challenge in developing the methodology from that point of view. But there are some synergies between the two, and we tried in our overall approach to exploit those similarities, trying not to overplay them, and on the other hand, not to underplay the similarities. And it's very important in the broader context of understanding these distinctions, and not to conflate proliferation resistance and physical protection, as some people do, particularly folks who are detractors of nuclear energy, try to use events or circumstances connected with one to say, aha, we've got a problem in the other area. They're distinct, and it's important to realize the distinction here as we've defined it. And as we've defined it, we've accordingly developed our methodology. So we have a charter. The charter was given to us back around 2003 when we started the activity. We formed a group appointed by the participants in the Gen 4 International Forum. And the basic idea is to demonstrate a methodology, develop it and demonstrate it so that one could be able to do assessments of PRMPP with three major tasks. One is to characterize in and of itself what the relevant proliferation and security threats are that we are concerned with for future nuclear energy systems. Secondly, to specify measures for expressing the system's proliferation resistance and physical protection. How good are we doing? What are the things we're measuring it against? And thirdly, to develop the methodology to assess the measures and quantify them. So, but very important in all of this is to work it in a consensus type of approach where all of the international participants are in agreement that, yes, this is the approach that makes sense to all of us, and that is what we've strove to do, and we work to develop a coherent approach to our methodology. So the major products of the group, and I'll reiterate this again at the end, is we've developed the methodology, and it's a document that's available on our website, shown at the lower portion of this slide, easily available to everyone. It's an open website. So the methodology is there. It's easy to find and click on. The second major piece is the example case study that we did, and I'll say more about that in a few minutes. And the third is what we call a comparison study. It's really comparing our methodology to where we stand with the 6 Gen 4 designs with regard to PRMPP. So, and those are three major documents easily obtainable from our website, and for those who would like to see more information, I strongly encourage you to go to that website and see these documents and hopefully read them and use them as you move forward. And along the way, we developed some supporting products, a bibliography, I'll say more about that later, detailed references for researchers, practitioners, and designers in particular. And we also developed a shorter document which frequently asked questions about PRMPP, and for people who just wonder about what is the subject, probably the least familiar of the 4 goals of Gen 4 and how we approach it. So this gives you a good idea in a nutshell of how you do it and what the further references are. So again, that's available on the website. And the other major product, the key product really in all of this, is our ongoing interactions with the Gen 4 designers. Because this is why we're doing this. This is why we did it. And I'll say more about how we've interacted with the Gen 4 designers every step of the way this activity. Now, in terms of what the value of PRPP to future designs, there are three aspects of that. The first is I'm a firm believer that you should use this methodology. The designers, whether they're Gen 4 designers or other advanced nuclear concept designers, use this methodology very early on in the design, right as the design concept is being formulated. Start to bring in PRMPP so that it's built in, it's not something that's retrofitted at the end of the design when one is going to a regulator or an international body for approval for the design. So it's important to work it into the design very early on. And what's the way to really approach that is to interact with the designers, the methodology, the methodologists should interact with the designers every step of the way, and as the design matures, the PRPP model would mature along with it. We call that progressive refinement. It's a bootstrap type of thing. As the methodology gets better, some insights come from the methodology. It goes into the design. The design is then advanced, and then methodological. The methodology, the methodological model is advanced as well. So it moves along with the design right to full operation, and it's continued to be used throughout that entire process. In fact, right into ultimately into decommissioning over the long term. And thirdly, the PRPP results could be useful to policymakers at the get-go in terms of informing choices about the designs and how one interfaces with regulators and other institutional bodies in terms of what's important for the design early on. So this is an opportunity to get these ideas at the forefront very early on. So in terms of an actual evaluation, what is needed, what should be considered, one, what are the policy directions? How do you formulate the questions in terms of PRMPP? What are you asking about the systems in terms of their robustness for PRMPP? In any scientific enterprise, asking the right questions is key. So that's the first very important step. So specific to PRMPP, it's the adversary context for threat definitions. What are the objectives of the adversary or actor? What are the capabilities of that actor in terms of economics, technology? And third, what are the strategies that the actor adversary might put in place to carry out the malevolent acts? Important is understanding the design in the evaluation. You need to, the people who participate in the evaluation have to include the people who know the system best, namely the designers. And so that design, as it relates to PRPP, is key to doing the evaluation. The overall fuel cycle architecture is going to be important in all of this, whether it's a once through or a closed cycle, or even something more global in terms of sharing, providing fuel and taking it back from between various organizations. So all of that has to be brought into account. The safeguards and security contexts are key here as well. You need to know what safeguards and security systems are being put into place in the design, and how those mitigating features help in terms of understanding how to thwart the objectives of the malevolent actor. And it's good to have some reference case baseline to compare to see how good one is doing in terms of, this is always true, of course, that how good am I doing? Is there some reference? Is it a baseline? Is it a set of goals that have been put forth? So that is important overall in an evaluation. So our methodology, and here it is at a very high level, basically it's a scientific approach. We consider our system, the PRPP system, and we ping it with challenges, just as one does in a scientific experiment. You want to understand some system, and you typically ping it in some way, probe it, and look for the outcomes. What you measure, what comes out of it, whether you're scattering particles or you're measuring temperatures here. Here we're pinging it with threats. We're looking at how our PRPP system responds, and we calculate and assess the outcomes. And in terms of system response, we have to consider two very broadly different aspects. One is the intrinsic design itself in terms of the physical features of the Gen 4 system, its technical design features. All of that taken together, we consider the intrinsic protection within the Gen 4 system. And then we have another piece that we call that the extrinsic. Those are the institutional arrangements that are brought to bear. If it's PP, that's typically the state regulator who would say, well, this is what you've got to do in terms of physical protection. You've got to assure the following. Or if it's PR, proliferation resistance, it's typically at least the IAEA, International Atomic Energy Agency, who provides the guidelines, and so that's another aspect of the extrinsic part. And these two, it's not additive, it's more interactive between the two, because the extrinsic will say something about what you should be doing in the intrinsic part, and vice versa. The intrinsic you'll see how well you're doing in terms of the requirements put upon the designer by the various organizations that come into play. And what one should be mindful of in all of this is that it's a very difficult area, in that proliferation, theft, and sabotage involve an intelligent adversary who could react to, even during the course of a scenario, in terms of adjusting. And so the human interplay is very important here. And so it was really competing adversary and defending forces, and that needs to be recognized in the assessment. So that makes it a very hard thing to do, but not impossible, but also very necessary. So this just turns that view graph over, going vertically now. We have the challenges going down, system response and outcome, and just blowing up the system response a little bit more. One needs to define what the elements of the system are that are of interest for PRMPP, for the full nuclear system that's being considered. The target identification and categorization, these are targets of opportunity for the malevolent actor. Then thirdly, it's getting an assessment of what actually happens in the system when it's being threatened. And our methodology has a pathway approach that we've taken. It's an inductive approach where one works one's way through the various possible states of the evolving states of an attack and how it evolves. And then one estimates the so-called measures, which I'll talk about in a minute. What are the outcomes? And these various pathways can be compared in terms of their importance, and one then assesses and presents the final results for consideration. This is just a quick look at how one would actually step through it in a 9-step process. This is in our methodology report. I won't read all the details here. You could see them as well in terms of the exact points that occur in each of these boxes. Basically, you need to frame the evaluation, form a study team, and I should mention that the study team has to be interdisciplinary, because we're looking at many aspects of a difficult problem. Decompose the evaluation and develop a plan for how folks are going to do the analysis, collect and validate data, and then do the big thing. Step 6 is perform the analysis, and 7 is to integrate and present the results. And these results get presented in various ways depending upon the audience involved in the information gathering. It could be at a high level, could be at the level of designers who have to modify results. Reports have to be written, and finally, and very importantly, key to all this is to have an adequate peer review, people who could validate what's been done and give guidance on how to improve the study where it might have shortcomings. And this itself is an interactive process and brings one back to probably step 5 again, and then until one really converges on a robust assessment. So let me say something about the PRMPP measures that I've hinted at. The group early on in its activity came up with its PR measures and the PP measures. We came up with 6 measures for PRPP, 6 for PR and 3 for PP. For PR, one is the technical difficulty of carrying out the proliferation activity. The time frame, second, the time frame for doing that, which includes the time in which one initially starts to plan, where the adversary starts to plan for a proliferation activity, and it could be a very long time. The cost to the proliferator, the probability of detection by typically the IAEA, very important, is number 5, the fissile material type. What type of uranium is it, enrichment, is it plutonium, what is mixed in with it, as a typical materials that we then, in our report, we talk about it at length. And detection resources efficiency, that's basically the cost of putting safeguards in place. We thought that should be in there as well in terms of understanding the robustness of a system with regard to PR. PP is very similar, but we're managed because typically PP is mandated by the state, and individually and separately by each country. So we've characterized it in terms of probability of adversary success, the consequences of that success, and the resources that the protector, defender would have to put in place to protect against the malevolent act. And these are then mapped into specific metrics, and you'll have to go to our report to see, if time does not permit me to go through all of that, but you can go to our report shown at that link at the bottom to see in each case what the recommended metrics, suggested metrics in some cases that we propose. Of course, each designer can come up with their own or fashion it to their own stylized need for their particular assessment. So those are the measures. And now the threats on the front end of all of this. So we developed what we call a threat matrix. I'll just look, in interest of time, just look at one piece of it, the proliferation resistance part. You could read on your own the physical protection part. And of course, this is all again discussed in our report. So we're looking at 4 broad features, namely the actor type, the actor's capabilities, the objectives of the actor, and the strategy. So you could see here, without going into lots of detail, it's obviously the actor is a host state. Resources are economic, technical skills, the possible nuclear materials, basic industrial capabilities, nuclear capabilities. Then in terms of weapons, it's a question of how many. Is it just one weapon? What is the or 10 weapons? What is the reliability of these weapons that are being fashioned? What is the desired stockpiling of weapons by the adversary, deliverability, how would they be delivered, and the production rate of the weapon. So those are mixed into the overall understanding, the objectives, and how to proceed in the analysis given whatever is specified in this. You might say, well, it's just one weapon, and we want to have a high reliability. It's not being stockpiled, of course. Then there's a question of how it would be delivered. So those things would be specified, and it would be part of the analysis. And then the strategies are important. Is the adversary interested in concealed diversion as opposed to overt diversion, where everyone knows that something is going on, but not taking very specific actions yet to thwart that. Is it concealed facility misuse, overt facility misuse, and then lastly, independent clandestine manufacturing of facilities based on Gen 4 systems. So that's a replication type of scenario. And then there's similar things with physical protection, which you could read in our methodology report in more detail. In terms of system response, as I indicated, we advocate a pathway approach, an inductive one, where one starts with assumptions about how the attack is going to be carried out. And what one does, and here's just a notional look at what a pathway scenario might look like. The key thing here is that it's being decomposed into pieces and then re-aggregated at the end to some finished result or a collection of results, ultimately, depending upon what the outcomes are. There may be various branches here. And ultimately, the pathways are basically potential sequences of events followed by the proliferator or adversary to achieve the objectives. And there may be obstacles along the way, and that would be a good thing. And what's important as well here is the time-dependent aspect of the problem and making assessments of the uncertainties. There are going to be lots of uncertainties in the analysis because, right from the get-go, the design is in its early stage, and also what the adversary might do is not precisely known, so that one needs to recognize these things and quantify that with uncertainty, or even at a qualitative level, get a sense of these uncertainties. And again, this is discussed in our report and how one would reflect this in an analysis. So it's not a final point number answer that one gets, but a range ultimately. So as I've indicated, between PRMPP, there are similarities and differences, and these are just quickly summarized here, and I think I've said some of these things already. So for the threats, we have diversion, misuse, and breakout scenario for PR. Similarly, for physical protection, we have material theft, information theft, and sabotage. International safeguards are key for the proliferation resistance, and domestic safeguards and physical security systems for physical protection are key. The PR tends to be slower moving events. They're planned. It might be a protracted diversion of materials. Whereas a physical protection event tends to be fast and it's an attack, but it's not always the case in each, and so one needs to be aware of that in terms of the analysis. And PR will definitely have international implications, violation, and certainly PP will certainly have as a minimum regional implications, certainly within the state in which the attack has occurred. So for what we recognized early on in our the methodology design development, is that probability of detection for a new system, particularly as one's introducing new safeguard systems, because the safeguard systems that we know are at IAEA are largely defined in terms of Generation 2 nuclear reactor systems. And here we're looking at newer systems, some of them not tried in any real sense, and how does one develop a safeguard ability, and how does one even calculate the probability of detection of a malevolent act? So we thought it would be useful early on to introduce a notion of safeguardability, which is defined by us as the ease with which a system can effectively and efficiently be put under international safeguards. So this gives us a figure of merit for the probability of detection. And it's a property of the whole nuclear system. It's not one system at a time, but overall it needs to be applied across the board to the entire nuclear system under consideration. And in terms of safeguards, this is now in the world of the intrinsic aspects, here's why you need to consider safeguardability, because there are differences. The accountancy tools and measures that we know for the Gen 2 systems may need to be modified for non-conventional fuel types. New fuel loading schemes may present novel accountancy challenges. And the accessibility of nuclear material could be different. You could have facilities that are operated continuously in terms of refueling, or you might have to just consider how is the facility refueled, what is the location and possible mobility of a facility. Could it even be, let's say, a floating nuclear power plant? And existence and location of other nuclear facilities nearby or in coexistence with the new facility. So these things need to be considered in future reactor safeguards. And I should say IAEA is giving a lot of thought to this and has produced various documents, which can be found in our bibliography, which I'll indicate a little bit later on. So, and just continuing, fuel leasing and supply arrangements that avoid on-site storage and or of fresh fuel and or used fuel need to be considered in these future reactors. Access issues for both the inspectorate and the adversary is important, and communication for remote monitoring by communication with the operator, state, and the IAEA. All of that will be new and being considered by IAEA and others, but this has to be part of the extrinsic aspect of the assessment problem. And for the physical protection side of the house, one has to consider, will this be different, and how might it be different, and how would it affect safeguards, international safeguards? What are the push-pulls between international and domestic safeguards in terms of, well, let's say material accountancy for one? Will the site or nearby sites have more or less ancillary equipment like hot cells, pin replacement capabilities, fuel storage, and research reactor activities? Will the containment be shared with multiple units? Will there be underground containment? All of this is very important for future safeguards. So in terms of developing our methodology, from the beginning, we recognized that we're starting anew. There had been, of course, some work done in previous decades, but not a lot, not at least as far as we wanted to go. And we thought that to carry out a methodology, to develop it and present it, we needed some reference guide for ourselves. And so we decided within the first year or so of our activity that we needed to develop an example model, not one of the Gen 4 systems, but an advanced system that some of us in the group were at least familiar with, and somehow that came out to be a sodium fast reactor. Several of us had previous experience one way or another with a sodium fast reactor. And one of the fortuitous things is that there was a design from the early 90s, maybe late 80s, that was put forth in the U.S. by Argonne National Laboratory called the Integral Fast Reactor, which no longer being pursued as it was back then. But we had the good fortune of group members from Argonne participating with us. They developed a genericized version of the IFR that we could then call the ESFR and use that as a test case for our methodology development. So we took training on this design with the help of several people at Argonne in terms of what that design is, what we should be looking at, and that was very, very helpful. So we were able to use the entire system as kind of indicated here. It's a 4-unit system, 4 300-megawatt electric reactors with a fuel cycle capability within. I'll show a little blown up version of this in a second. But basically, we wanted to confirm the applicability at different levels of design detail, provide examples of how our methodology would be useful for the future systems, and also to help us, guide us in terms of where we should be shoring up the methodology itself. And we did some of that. So here's the ESFR in a little bit more detail in terms of flowchart. You can see the four 300 megawatt electric reactors. Here's a fuel cycle facility. Some of the others I won't go into in detail, but again, you could look at, and I strongly encourage you to look at our case study report on our website. It'll give you a lot of detail of how we carry out the study, and the scope of it was we considered, and this is the entire group, there were probably about 15 or 20 people in the group attacking different parts of the problem from the point of view of concealed diversion of material, concealed misuse of the facility, breakout scenarios, and overt diversion and misuse occurring. And for the PP side of it, we looked at theft of weapons usable material and also sabotage of the facility system elements. So we looked at all of that, and again, there's a lot of detail in the report. But I'll just tell you what our lessons learned were broadly from this. First and foremost is that the methodology can be applied during the conceptual stage of system development. Secondly, completeness and identifying attractive targets and pathways is important. They can be identified and as one progresses with the analysis. Now, very important is third bullet item here, third major bullet item, is that, of course, when you start looking at a new system, there are going to be uncertainties, or you're going to have to make some assumptions about how something behaves or how something is protected. And the way we regarded that is that when you make those assumptions in the analysis, and if it's a major thing, we then think of that as a functional requirement for the design basis, and you need to document that, and then that becomes a requirement. So in other words, if you want your assessment to come true, you have to make sure that you've met that functional requirement, which was a basic assumption. Now, of course, you could change that assumption if you can get a better answer, or you could relax it, or if you think it was not strongly relevant, or you have some other way of achieving your goal. But that was a very key thing there, that these assumptions need to be documented and recorded. So the assessment requires considerable technical expertise broadly, and we recognize that. Fortunately, in our group, we had some broad expertise across the various countries and organizations that participated. And we also recognize that some standardization would be needed in the future as the methodology progresses with further case studies or actual studies that we envision being done by the system designers of Gen 4. And lastly, what's very important is that we obtain insights along the way in doing the analysis. One does not have to get all the way to the bottom line results to say, aha, I now know how this thing is operating or how it can be protected. But early on, one could even find aspects of the design or insights about it that can then be implemented to improve it. So that's a very valuable part of the activity, and we found this to be the case. So let me turn now to the workshops that we carried out with the Gen 4 designers and with others. We opened our workshops to all who were interested in the various countries, the Gen 4 countries. We were not exclusive in this, but ultimately, the objective here was to inform the designers of what we're doing, and to hear from them, more importantly, to hear from them what their needs are in terms of our design activities. So it's a dynamic activity between us. So the near-term objective is to focus the methodology towards the system development needs, generate insights concerning design and operation, to enhance the performance with regard to PRPP. Longer term, to establish beneficial PRPP-related design and operational principles and practices, And then supporting all of this is to establish a good working relationship between the experts in the PRPP working group and the designers. That's something we continually work on. As you can see at the bottom of the slide, we've had 11 workshops in various locations, and we intend to have more as time goes on to get people involved with what we're doing and get that dynamic interaction. So it's getting the designers to become familiar with the capabilities and limitations of the methodology and identify techniques and procedures to enhance the application of the methodology effectively. So Gen 4, of course, many of you have seen this. Gen 4 sits here on the right. The beginning of it all was with Gen 1 back in the 50s or 60s through 70s. And then we have the big growth of nuclear power worldwide, where we now stand with 440 or so nuclear power plants, and now we've already embarked. We have some Generation 3 and Generation 3 Plus plants that are actually operating. Some of them are being built, and some are yet being designed. But our focus is on the 6 Gen 4 designs, which are indicated here: the sodium fast-cooled reactor, the very high-temperature reactor, gas-cooled fast reactor, supercritical water, lead-cooled fast, and molten salt reactor. They all share one basic thing in common, and that's their architecture. On the left-hand side of each diagram there, you see where the nuclear energy is being generated, typically in a reactor core, and a fluid is heated. It's transported by a plumbing system, ultimately, typically to a turbine, which then cranks a generator, and out comes the electricity. So the basic idea is the same in all of these, but the working fluid's different. The way the neutronics works its way out in the reactor is different in each case, and that's summarized here. Now looking vertically downward, we see the neutron spectrum very quickly, the coolant, the working fluid for heat transfer, and the possible range of possible fuels. This is from a 2009 annual report of Gen 4, so some of these might have changed a little bit. Refueling modes, whether it's online, offline, and fuel cycle, open and closed, or open or closed, and then the power of the reactors, the range of powers. PRPP is mostly concerned with possible fuels, refueling modes, and the fuel cycle. So those are the three real focus elements for PRPP in terms of where the analysis will vary from, of course, with different fluids. That will impact the analysis as well, and the spectrum of the neutrons. But the fuels, refueling, and fuel cycle are key to the analysis. So as a result of workshops that we held with the system steering committee that manage the 6 Gen 4 designs, that's the acronym SSC here, which I haven't spelled out, I don't think. We worked with them back starting around 2007, 2008, 2009 in a series of workshops, or 3 or 4 workshops that we had. We were working with them on trying to develop white papers with each of them, jointly co-authored by the PRPP working group and each of the individual system designer groups for each of the 6 designs. And the basic idea of the white paper, indicated on the right-hand side of the view graph, is what is that technology, what is its fuel cycle, what are the PRMPP targets and adversary opportunities, what are the scenarios of concern, how one might protect against PRMPP, and then finally, what are the open issues, what are the needed R&D elements for PRMPP for each of the specific designs. And that report was published again on our open website. You're all encouraged to read it at that link. It's got 2 parts, each 6 white papers jointly written and approved by EG and PG of Gen 4 and each of the design groups. And the first part of the report is actually shown on the left-hand side of the view graph. We basically set up what our objectives were, how the workshops were conducted, and some of the cross-cutting issues in the amongst the various designs, fuel type, coolant moderator, refueling modes, just the things I mentioned earlier, safeguards topics. So again, I encourage you to read it. I should also tell you that we're in the process of updating all of this with the system designers. We've embarked on, I would maybe call it phase 2 of that overall activity. We're looking afresh at where we are today with the Gen 4 designs, where the methodology is today. How do we talk with each other? And we've already had a major workshop on this just about a year ago at Paris. And we're embarking on updating the white papers, trying to figure out how we might start to take a deeper dive with a few of the Gen 4 designs in terms of implementing key aspects of the methodology. So this is happening. It's good that it's happening because people change in the PRPP working group over the course of the years. People change in the designer groups. So to some of, in both cases, it's some of what we've done back 8 years ago, 10 years ago, is new people are involved, and they need to come up to speed and understand what we did and help to carry it forward as we move on. So in all of this, what will designers and analysts actually do? At the outset, I should say it's a team effort, multidisciplinary team. You've got to bring key to all of it is the designers who have to really take ownership of this activity using the PRPP tools to improve their designs, bring it in early on in the analysis. Safety analysts would be helpful here too, because there's a safety safeguards interface. We didn't invent it. It's been there long before we came on the scene. It's always been an issue or a topic of interest in any nuclear concept. Safeguards, security people need to be involved as well. Got to get an IAEA needs to participate in some way in this, or people trained with safeguards need to be involved. Security analysts need to be involved, and analysts more generally in terms of folks who can carry out the pathway analysis and get to the quantification. Some of it involves expert elicitation, because we're going to encounter here new areas where expert opinion needs to be brought to bear and put into the assessment. So human factors analysis analysts are going to be needed here as well. So it's a big team that needs to be involved. So early on, one starts with the plant models at a block diagram level, and similarly one would have PRPP models at a block diagram level, and then as I indicated earlier, progressive refinement would occur, and we would bring the models up to date as the designs mature. And very important to all of this would be interactions in the sense of the broader team with the regulators, with the IAEA as appropriate to the designs. In each country it's different, and IAEA has its own views on what, to the extent that it would be involved in such studies. As I understand it, they're very interested in, and to the point on that, IAEA has been promoting what they call safeguards by design, international safeguards by design, which is really a subset of PRPP by design. So they've developed documents which are indicated in our bibliography for that very aspect of it. So they're strong advocates of getting involved early with designs, getting involved with regulators early on, and the designers, and it all moving forward in a cost-effective and efficient way. So I mentioned that we have a frequently asked questions document. It's actually a small trifold. You can fold it up and hand it to, one page, but fold it in three. That's what trifold is. And what we did was we came up with, as indicated here, 17 questions. So, like, what is PRMPP? What is the form of the result? I'm just picking some of these off here, not going to read them all. At what stage of evaluation should PRMPP evaluation be performed? And so for each of these questions, there's a short paragraph type answer with, as appropriate, references to where to get further information. So if you're not familiar at all with what we're doing, maybe this is a first step in terms of getting a better idea of what PRMPP is all about. And there's the web link, the easy web link to that. But again, you go to the major website of Gen 4, all of this will come out. In fact, I think it's highlighted on Gen 4's open cover page. The bibliography that I mentioned here, this is a little bit more lengthy document, but it's essentially a collection of references broken up into essentially 5 sections. One is our official reports that we've written and our deliverables. Some of them have been translated, by the way, into non-English language. So I know for a fact that the Japanese have translated these the PRPP reports into Japanese for the use by their designers. And there may be others, but in any case, we have a section on PRPP articles and papers that have been collected over time on applications. Be interesting to people to see these, get a sense of how you might do some of these analysis. And then we have papers and articles by members and non-members, but using the PRPP methodology. So it's an interesting thing that we found that not only has PRPP been looked at within Gen 4, but folks outside of Gen 4 have seen our open literature papers that we've done the conference presentation and said, gee, yeah, this is very interesting. Let me try it. And they have. And so it's gratification and validation, I should add, from that people have been able to pick up our methodology report, read it, and then apparently understand it and use it and get results. So without coming back to us and saying, could you explain what it is, what this uncertain thing that you've written here, they've been able to carry it out, and we've seen the results of their activities, and pleased to know that people can take this work and actually use it. And so there's been value outside of Gen 4 as well. So, and then there's just a broad collection of papers on the subject matter in Section 4, and then Appendix A has IAEA papers and documents that are related to PRPP, and an aspect is in their INPRO activity, their advanced reactor activity that they've been carrying out for several years. Important to all of this, key to all of this, in fact, is the folks who've made PRMPP happen. I just have the honor and pleasure to tell you this story, but it came about because a lot of people worked very hard over a decade and a half. Now, I don't have a picture large enough to show all of them over that 15-year period. I wish I did, but here some of them are indicated in this workshop that we had. But everyone deserves acknowledgments for this truly international effort, which really is a lot of collegiality. You can see the countries and organizations that participated. So I'm just very thankful to everyone who participated over the last 15 years in this activity. So major accomplishments, I've already said this a few times. It's the methodology report, the case study report, and the joint efforts with the 6 system designer groups. And again, they're available at that website, shown here one more time. And just as final notes in all of this, it's not just the bottom line results that you get out of a PRPP assessment that's important. And it is important to get those bottom line results, but it's the insights that you get along the way from doing the assessment. It's a disciplined process. It gets you to look at every stage of what you're doing, and sometimes early on, and I've been involved in various studies in safety and non-proliferation over the years, and it's typically the case that you find out early on that, aha, here's something that's very interesting, and it informs our design, so it's very helpful. Secondly, as I've been saying, do these studies, start them now, early in the design process for the full nuclear energy system. You're definitely going to benefit from it. You don't want to wait until everything is built and then say, gee whiz, I've got to go ahead now and do a PRPP analysis, and then the regulatory body or the IAEA comes back and says, well, you know, you got to change your system, and then you find that, well, yeah, I'm going to have to move a wall, or I'm going to have to do something else, change out something, and that becomes very costly and incurs time delays. So doing it early is a good thing. And finally, don't do just one report and say, aha, I've done it. I've done my PRPP analysis. I've met my checklist requirements. I'm done. It's not. You've got to, it's a journey. You've got to keep doing it. It's a living study, a living document throughout the full life cycle of the facility. And so I encourage all of this. Thank you for your attention, and I'm happy to receive questions now.
Thank you, Dr. Berry. If you have questions for the presenter today, go ahead and please type those into the Q&A pod, and we will come back and get as many of those as we have time for. While those questions are coming in, let's just take a quick peek at the upcoming webinars planned in the Gen 4 series. In June, a presentation from Dr. Ignatiev on molten salt actinide recycle and transforming system with and without thorium-uranium support, otherwise known as Mozart. In July, a presentation on Astrid, the lessons learned by Dr. Varane with France. And in August, a presentation on BREST 300 lead-cooled fast reactor by Dr. Rakov with the Institute of Power and Engineering with Russia. Dr. Berry, are you able to see there's the first question?
No, I see something called presenter chat down in the right-hand corner. Do I have to click on something?
In the Q&A pod, there are
Oh, I have to find the, oh, no, I don't see anything in the Q&A part. Oh, let's see. Okay. What do I see?
To the presenter view, if you scroll over the...
Right. Yes, I do have that now. Yes.
The first question is how is the use of blankets perceived?
Okay. How is the use of blankets perceived in the PRPP space? Okay. So I'm trying to guess that I'm going to assume that we're talking about blankets in a breeder reactor. Is that what the questioner is asking about when he said blankets? So I would just say that it has to be part of the integral analysis. If you do have blankets in your reactor which have material that you're going to breed or fuel from, and in fact in our case study you can go back and look at that. You can see that we looked at some alternatives, and if not right in the case study report, we certainly have some follow-on documents that are in our bibliography. So it needs, so perceived is, yes, it has to be analyzed to get a full picture of what's going on, because obviously there are going to be materials of interest that are going to be in those blankets as time goes on. Okay, next question. Thank you for a very interesting and significant presentation. So I don't think there's a question there. It's just a thank you. I accept that. Next question from Dr. Kosinov. Which of the Gen 4 reactor design is most promising in terms of PRPP aspects? I would say that they all are. I'm not. There are no winners and losers here. I think they all show features that are certainly promising. We're basically encouraging analysts and the designers to continue on with their efforts, because I think we have 6 good designs there from PRPP point of view, and we need to just make them better and make sure that the PRPP goals of Gen 4 come true when the analysis is completed. Okay, next one is a good question coming from Dr. Koyatsu, who's one of the co-chairs of the PRPP group and a long-term contributor to what we have today in terms of PRPP. So, and he's asking, how long will a PRPP evaluation take? He asked me a few questions. What effort is needed? 3 questions. Can the methodology be simplified? Okay, good questions from Giacomo. The evaluation should progress in stages. I would guess that within a year, some good results should be coming out of PRP analysis. Again, it depends upon how much time. You know, it's not just time. It's how many people are crunching on it at a given time, and how many people are on the design side and on the analytical side from PRPP point of view. So you can get some quick results early on, several weeks to months. You get some very preliminary information. But as we did indicate this time parameter in our frequently asked questions, so there's a little more detail there. But I would say that start now. Do these things, and it'll be it should be a living document, and you'll start seeing value in it fairly early on, within months, maybe sometimes in weeks. When we started our case study, we found value almost right at the beginning. It was kind of interesting. We looked at, how can we divert fuel? And we saw that LWR fuel assemblies were coming into the plant, and we said, well, why don't we just divert those fuel assemblies before they get to the plant, or as they're being received in some way? And so that was eye-opening to some people, that would be an avenue of opportunity. So and then it suggested, well, we need to be mindful of the fact that needs to be protected. So the second part of that, what is the effort needed? Again, it needs, as my view graph on the team that has to be put together, you need, and I guess this ties in with the first question, you need at least 3 or 4 people who've got this activity on their mind for at least quarter time or half time, ideally full time. So it could be a few staff years, measured at least in staff months to start moving it forward. You need a critical mass of people, and you need at least 1 design person, 1 or 2 PRPP people, and someone who knows about safeguards. So you need them regularly available to do things, ask questions, provide answers. Can the methodology be simplified? That's a very good point, too, made by Giacomo. We've thought about that, how to simplify it. And I think the key is in the progressive refinement approach, that if one is indeed starting with the designs in their early stage, which all of them really are, if you start developing block diagrams of the systems, and maybe take our case study as a cue here, start developing block diagrams for PRPP, I think that can be helpful in terms of at least understanding what how much depth one should be going into, and this can come from actually doing the analysis. The more people we have doing these analyses and reporting on them jointly in let's say, an expert groups meeting of Gen 4, giving other people insights as we develop a cadre of people who are working collegially in this area, I think it will help. People will learn about shortcuts in the methodology, what pieces of it can be done more efficiently or effectively. Let's see. Next one is Alice Campaniti. Thank you. You mentioned interest in safeguards by design. A newer concept being discussed, at least in the U.S., is security by design. That's a very good point. Thank you for that, Alice. Can you share your thoughts on security by design and approaches that states might wish to follow to develop standards? Yeah. So there is an interest in the U.S. on security by design. There's been efforts that the regulator have been interested. The NEI in the U.S. has been interested to a certain degree in this area, and at least almost a decade now, there have been a series of workshops on how we can bring to bear analytical methods, something akin to what's called probabilistic risk assessment, to the security area. Of course, the security area is more challenging, as indicated in my talk, than the safety area, where it's an episodic event. There is no malevolent actor there, hopefully not. So some progress has been made in the U.S. People have, but we're not there yet. But I'm certainly an advocate of moving that forward. Hopefully, with I believe there are in the U.S. there are a few, or at least one or two plants that are piloting some efforts. I haven't been close to it lately. The other trick in all of this is when you're doing a security analysis of a plant by design, and in fact, if you're doing it when the plant is fully operating, you're dealing with a lot of sensitive information, and that's always a challenge here in terms of getting things standardized, getting it discussed openly and broadly. So, in fact, that applies to all of PRMPP, because ultimately we're butting up against the area of sensitivity, and we talk about that a little bit in our report. There's no easy solution to it. So international standards would be great in this area. I think they're, to the extent they can be done, it would be definitely helpful. Next question, do you think PRA can be applied to PRPP evaluation? Yeah, that's a good point. Some of us, I have to reveal a secret. I spent more of my life doing PRA for accidents than PRPP, but I've been thinking about PRPP for the last decade and a half, a lot more so than I've been talking about accidents, thinking about accidents. And the PRA, you can't just translate the whole PRA machinery into PRPP, but there are elements of it that are very good for PR and PP, for both sides, PR and PP. The PR side of it, certainly scenario development, looking at, in fact, what we did was early on when we did the case study, we looked at what type of approaches could be used. Can we use event trees or accident progression trees or variations of it, accident delineation models. We looked at a host of them. Some folks looked at success trees. We tried a bunch of things. And if you look in our report, what we say about pathway analysis, we leave it to the designer to choose that. We're not being prescriptive about what you ought to do. We were saying here are a few ways to do it, and we talk about them. And in fact, in my own work with colleagues here at Brookhaven, we've used Markov models to look at both PR and PP, and that you'll find those in that bibliography that is on our website. Next question is it expectable to see PRPP imposed by regulators to NPP in operation? Oh, gee, no, I don't expect it. Regulators to impose it. In the U.S., we don't even impose it on for the PRA, except, of course, for new plants. We do say that you should do a level 2 PRA for the new plants in design. PRPP, I guess, for the PP part, I guess this follows on. So whatever I've already said in answer to Alice Campaniti's question, that applies here. So to the PP side. For the PR side, I don't see the IAEA, at least my vision, which is not 2020 in this area, and I don't have perfect vision into what IAEA is thinking as a full organization. They have to speak for themselves, of course, but I don't know that they would then say you've got to use the PRPP for moving forward. But they are saying that they're encouraging safeguards by design, international safeguards by design, which is and again, look into our bibliography. You'll see some of the documents on that, on safeguards by design, or even more easily, just Google safeguards by design, and you'll get some sense of where IAEA is right now on that topic. Okay, so I think that covers the questions. I'm happy to receive more or a second round from the people who've asked if I haven't answered your questions adequately. Well, good questions, by the way.
I don't see additional questions coming in. Thank you, Dr. Berry, again for your presentation. Very informative. Thanks, everyone, for attending. Your participation is greatly appreciated.
Thank you so much, Bob. It was very interesting. Thank you.
One more question. Let's see. Okay, it was just thanking me. Okay. Fine. Always nice to be thanked. Can't argue with that. Well, thank you. Thank you for allowing me to do this. Well, it's an important thing, and I'm very glad that I had the opportunity to do this.
Yeah, and as always,